All right, hey people watching this video, this is 7-3 notes. We're going to get through the first just couple of examples, but before we move on to 7-3, because this is the last section, I want to kind of review over 7-1, 7-2, and what those looked like, okay? We were in 7-1 looking at proportions, okay? What symbol do we use for proportions? Proportion, like percentage, like this percent of people between here and here. What symbol? P. P goes in the middle, right? We're doing P, okay? And then we still have an error that we're adding and subtracting. So over here we subtract the error, over here we add the error, but what are we adding to? Do you remember what that symbol was? What? Nope. What? Nope. Mu is average. What's the other thing that we use for P? Nope, that's average. P hat. P hat is the sample P, right? Okay, this is the population P, sample P is P hat. So those are the symbols that we use. And to find the error, I'll give you this, is Z times the square root of P hat, Q hat over N. Do you remember doing that, guy? That's the error that you're adding and subtracting each time. But you're trying to find that interval. That's it. Like, that's all that it boils down to. Okay? Good. This is just kind of a summary of stuff. We will eventually write this on your yellow sheet. But just so that we're clear, you know, like going forward, you kind of can see trends going on with these three sections. Mean is what we just got done doing. What symbol goes in the middle when we're making our interval? Mu. Okay? And we add the error and we subtract the error. And what do we add and subtract from? The other mean, which is called X bar. This is the sample mean. So to find the population, which is this guy, we add and subtract the error from the sample. To find the error, we do Z times S over the square root of N. And I'm also going to put in here that sometimes you will use T instead of Z. And sometimes you will use sigma instead of S, right? It just depends on what you're given in the circumstances, right? But those, your same formula, it's just using which standard deviation they give you, the population or the sample, right? Okay, most of the time it's going to be the sample, but that's how that works, okay? So that's the formula that we use for mean, right? Okay, for variance, it's a variance and standard deviation is going to be a little bit different, okay? So for variance, I'm going to do this one here. Variance, standard deviation, okay? Variance, the symbol that we use. Actually, let's go to standard deviation. What symbol do we use for standard deviation? What guy goes in the middle there? Sigma, right? That is standard deviation. That's the middle guy. So what will the variance middle guy be? Sigma squared, right? We know that the variance is the square of the standard deviation. Do we know that? Yeah? Okay, then the formula that we use is really super kind of ugly. Go back up. Okay, I'm just going to write in the standard deviation formula, and then we'll talk about the variance one. But standard deviation is kind of an ugly formula. This is the only time, put a little star that says do not plus minus error. Okay? This is the only one that you're finding. We did proportion, we did mean. Variance and standard deviation is the only one that you're not finding an error and adding and subtracting it, right? This is the only time this doesn't happen, okay? So the formula for standard deviation is the square root of n minus 1 times the standard deviation squared over chi squared right. You don't know what any of this means yet, but you will. And minus 1 times the standard deviation squared over chi squared left. And I did do that on purpose. The left one is on the right and the right one's on the left, and I'll show you why that is here in a second. But that is the formula that you use. Okay? All right? It's not scary. Okay? It looks like an X, yes. That's the symbol that you use. Chi squared is what he's called. Chi squared left and chi squared right, okay? Don't get discouraged. This is really super easy. It's just as easy as the other ones. Chi squared left. It's just the number from the chart that you use. It's just the numbers from the chart that you use. Your x. Okay, so x is like that, right? Squared, and then either left or right. That's how it looks. The symbol. It's just an X. It's like a capital X. Okay? Huh? Yes. Yes. That's standard deviation. Okay? All right. If that's the standard deviation formula, what formula do we use for variance?
No square root.
No square roots, right? So I'm just going to do no square roots if we're doing variance, right? You don't take the square root if you're doing the variance. Standard deviation is with the square root, so that's why I'm writing that in there. Okay? Good? Yeah, not too bad. Okay, let me show you how this works. Oh man. Let's go down to the formula here. This is what we just had, what we just wrote down. Let's talk through some of these variables. So go to this box, which is halfway down the page. We're skipping example 1. We'll come back to it. But let's write down some of this stuff that we have. So N. What's N stand for? The number in sample. We're used to finding him. He's the easiest one to find, right? The number in the sample. What does S stand for? The standard deviation. Which standard deviation? Just wait. But we're going to write it in so you remember. Which one? The sample, right? What?
Go up a little bit.
No, I don't want to go up a little bit. We're writing it in. We're writing it in so you remember. Okay? Now, chi-squared right and chi-squared left. In the first example, they're going to have us do this. And there's a reason why the right side one is on the left side and the left side one's on the right side. You take them and you flip them, right? Do you notice that? Right is over here, left is over here. That is not a typo. Okay? All right, so here's how this works. Everybody watch. The right side number is going to be a bigger number. The left side number is going to be a smaller number. These are numbers that you look up on the chart. Okay, this is the chart thing, right? So not Z, not T. These are the numbers you look up on the chart. We're going to do the chart thing here in a second. Okay? Now, if you take a number, like that top stuff, and you divide by a big number, versus taking a number and dividing by a small number, what happens to those numbers? Like if you take a number and divide by a big number, this guy becomes smaller and this guy becomes bigger, right? Do you see how that works? If I take a number, like let's say I take 6 and I divide by, we'll say 100. 6 divided by 100 is 0.06, yeah? Okay, now I'm going to take a smaller number. Let's say I take 6 divided by 10. 10 is smaller than 100, right? What's 6 divided by 10? 0.6. This guy is bigger than this one, right? So if I'm dividing by a big number, I get a small number. If I'm dividing by a small number, I get a big number. Do you see how that works, right? Okay, so that's the reason why the left and the right are crisscrossed, okay? Because you want to divide by the big number on the left and the small number on the right, okay? Let's figure out what these numbers are. So let's go up here to the top into this example. A simple random sample of 22 IQ scores. What does that mean? Write it down. N is 22, okay? Are obtained. Construction of a confidence interval for the the population standard deviation requires the left and the right critical values of chi-squared. That's what he looks like. He's an x squared value. X squared means chi-squared. Corresponding to a confidence level of 95%. I'm going to say confidence down here. 95%. Write him down somewhere. And a sample size of n equals 22. We already wrote that down. We want to find what the chi-squared left number is and what the chi-squared right number is. All we're doing is writing stuff down. We're just finding these two numbers off of the chart. This whole example is just finding those numbers on the chart, okay? Normally when you're looking numbers up on this chart, you're looking up one number. This time is the only time that you look up two numbers, okay? So you want to go to the chi-squared side. It's the opposite of the T chart. It looks like, let me go all the way down. It looks like this one. Nope. This one right here, chi-squared, okay? And do you remember when I told you to write this stuff down and you have a 99.5 and you have a 99.5? You have two of them, right? You have a 99 and a 99, and then they meet in the middle at 90%. There's two of them, right? Okay, the left one is the left one, the right one is the right one. And then, what number do we look up on the side? This guy says
21.
degrees of freedom.
21.
Okay, N is 22. Degrees of freedom, still the same.
What?
N, it's still the same as the way we calculated it before, right? 21. Confusion? If N is 22, our degrees of freedom is 21. Yeah? So we go down to 21 degrees of freedom, and do we do 99%? I forget already. 95, thank you. 95% is this column right here and this column right here. Woo. Okay, we want to go 21. 21 is 11.591 and 32.671. These are huge numbers. A lot bigger than the Z and T. That's on purpose because we end up dividing by these numbers, right? Okay, so on purpose, they are bigger numbers. Do you guys see how we look those up on the chart? Degrees of freedom 21, not 22, and then 95%. Okay, somebody write those numbers down and then repeat them to me when I go back up. Okay, you got them? 11.591 and 32.671. Put that on your left and your right, and then I'll get them from you again. Okay, go back. 7.3. Where are we at here? 7.3. Here we go. Which one's the left one number? 11.591. Yes. The right number is 0.671. Now, the left and the right, when we calculate the interval, will be switched. But here, the left one is the left one, the right one is the right one. So in the formula, when we go down here to here, Erica, do you see this? The left one goes over here. So this would be your 11 point whatever, and this would be your 32 point whatever. Does that make sense? Do you see how they're switched in the formula? So the left one doesn't go on the left in the formula. The right one doesn't go on the right in the formula, right? Okay, but when you get them off the chart, the left one is the left and the right one is the right. Right. Make sense? Clear as mud? What? 21. Good. Degrees of freedom is always one less than your N, right? Because we never want to assume more accuracy than we are able to. So by subtracting one, that reduces our level of accuracy, and then it makes it so that we have accurate numbers. Okay, we never want to assume more accuracy than we have. So degrees of freedom is always one less. Make sense? Good? Yes? Okay, let's go down and do an example and then we'll stop. Oh no, wait. We'll wait and save that example for tomorrow. But hold on, just wait a second. This is really super important because I'm pretty sure it has something to do with like question number 1 on your homework assignment. Ready? Okay. We will eventually be building confidence intervals that look like this, right? And we get number here and a number here. Okay. Let's say, just for example, let's say just for example, I'm like making up numbers here. Let's say that this guy ends up being a standard deviation of 6.5 and this guy ends up being 11.2. Okay, let's just say theoretically that my standard deviation is between those two numbers. That's what we get as an answer, right? Here's the deal. We did not add the error and subtract the error to get those two numbers, right? You don't do that. You don't do that. You found it by using the formula, which means this guy is not the exact middle. Does that make sense? Ooh, right? Ever before, no, you won't, okay? But ever before, that guy was exactly in the middle because you were adding the error, subtracting the error. It is not found that way for standard deviation, right? So he will not be the exact middle number, right? Keep that in mind for when you do a couple of your homework problems, okay? Good? All right, there you go. We'll finish the rest of it tomorrow.
Can you go back?
Yep.